Okay, ladies and gentlemen, good afternoon. Let me see what's going on here. Okay, yeah, we have our sound, which is good. Let me go to the browser for you guys here. Okay. You guys are not statistics. Let's go to 262. And I want to mention something here to you guys. That when I go to the worksheets and videos for 262, no, that's not it. I want to go to statistics online transition. It's 261. Let's go to 262. Oh, I have to go home maybe first. Go to this online transition now. We have some of these topics here. Parametric equations. So what I'm going to need to do is a couple of things. This is actually a summary because we then go to what's called calculus of parametric equations. There's a calculus version of everything we're doing here. But you guys first have to learn about parametric equations. So this is a summary of it. But I think what I have to do first, I'm going to have to introduce parametric equations to you from like 241. So this is the parametric equation form to start to do calculus of parametric equations. So I'm going to have to go all the way down because I don't think people know what parametric equations are. So if I were to ask you guys know what parametric equations are? It's kind of introduced in trig, but not necessarily. I think it's optional in a trig course. I think it's optional in a pre-calculus course. Has anybody ever seen parametric equations before in your life? Do you guys know what I'm talking about? Have you ever seen them? Parametric equations? Okay. What are you guys at home as well? Have you guys ever seen parametric equations? So here's what I'm going to do for you guys. I'm going to introduce to you parametric equations. But I'm going to import this into where I need to import it. So let me find it. Okay, here's parametric equations. And I'm going to import that into Notability. So I'm going to create a new note. I'm also going to go to the Calculus 2 version. Where are you, Calculus 2? So where are you? It's in, yeah. Oh, I forgot. It's in the online transition. No, what happened to it? No, I don't think that's it. There it is. Okay, so let's go to the iPad and see what we have. So I think I want to look at this first before we look at the trig versions of parametric equations. Have you ever seen that before? I'm just curious. See, here's the deal. Here's what's starting to happen. What you're looking at is what's called the Cartesian coordinate system, the XY plane. That's the regular plane you guys see in algebra. And what happens there in algebra is simply there's a lot of curves we learn how to plot, like circles, lines, parabolas. You guys know what I'm saying? Log equations, exponential equations. There's plenty of curves that we learn how to draw there. However, the truth is there's a lot more curves that you can see because that kind of algebra, we're very limited with, with what we represent and how we sketch curves. It's a very limiting environment, believe it or not. You may disagree. You go, no, we got polynomial functions, rational functions. There's a lot of graphing that we have done. But as we start to look at graphing from a little different perspective, what happens is we open the door to other kinds of curves. So what we're doing here is it's kind of a transition point. We've done a lot of calculus in Calculus 1 and Calculus 2 so far. We've done things like find area under curves. We've found volume, surface area. We've even found, derivatives of functions, tangent lines, and all their applications for a lot of, functions. We even looked at inverse trig functions and all that stuff. Let's close that door because it's kind of noisy. If we can, we'll just close the door. Thank you so much. Yeah, thank you. So now we're going to introduce another way of drawing curves. And so what you see here is the letter C for curve. Okay, so we kind of call that C. So you'll see parametric equations in Calculus 2 in terms of, two variables, really, the x variable and the y variable. And here's all you really do. We let the x coordinate be a function of a variable t. And we also let the y coordinate be another function of our variable t. So we introduce another variable is what I'm saying. That's called the parameter. And a lot of times that t variable represents time. So, we can start to really kick things up a little bit. And this is supposed to be a comma. I already noticed a typo. That's an ordered pair in the Cartesian coordinate system. Your rectangular coordinate system, it's also known as. And here's a point, right? Just like from algebra, you got an x coordinate, you got a y coordinate. We call that some point t. But your x coordinate is a function of time t. So sometimes, and I can already see another, God, I got to fix that. That's f and that's g. So x is a function of t, y is another function of t, t is in some interval. So I already found two typos to fix. Parametric equations, I got to do that. And then let me give you guys another idea that we're going to have to work with. Okay? Because t is in an interval, t, could be in some interval like a, b. Okay? It could be a closed interval. It could be, from negative infinity to infinity, your t value. And so what you'll have here, this is defining t in terms of a closed interval. You have the definition of what we call an initial point, IP. And we say a curve has an initial point at f of a, comma, g of a. So, the a value is like the starting point of the parameter t. Okay, this a value. If I can get a highlighter. So, we call that the initial location. The b value is the larger value in the interval. And, that's called your terminal point, TP. So I don't know if I have a picture here, but whatever. It's kind of like something like this. If I said to you, okay, we're going to use some value A, over here would be that initial point. And maybe you got some other value over here called B. So then over here, wherever we're at, That's a terminal point. Okay, so here's my A, and then here's my B. Initial point, terminal point. Okay, now initial point is like starting point. It's where you start. Terminal point is where you end. So there's going to be something that we're going to work with known as the orientation, because t is increasing. Your a value, your t, notice that how we write this interval, a is less than or equal to t, less than or equal to b. That means it's an increasing value for t, really. And so we have this, what we call orientation. If this represents like a path, and sometimes it does. So we have this curve having a particular orientation. That's why they call it initial point and terminal point. And we draw those arrows to represent what's known as the orientation of the curve. And that's going to be a factor in your life as well. Now, in Calculus 3, like I started to mention, Calculus 3 gets to work with parametric equations all over again. But in that setting, there's 3 variables, x, y, and z. Calculus 2, there's x, y. So you start to see this in Calculus 2, 2 variables, x and y, your Cartesian coordinate system. But then you kick things up in Calculus 3 to 3 variables. So you get to do calculus in 3 variables in the future. That's why you're supposed to know how to differentiate and integrate in Calculus 1 and 2. Because when you get to Calculus 3, you're doing it in 3 variables. So if you can't do it in 1 or 2 if you can't do it in 1 variable, you can't kick it up to 2 or 3, really. You guys know what I'm saying? It's called multidimensional calculus. So that's kind of the idea. And some of the instructors would complain and go, hey, we got instructors in, students in Calculus 3 not doing Calculus 1 or 2, because you got to do things in 3 variables. So you'll see this again, in 3 variables. And you'll have initial point, terminal point. It's now in space, 3-dimensional space. And that represents a path of a curve. That's why they use a parameter t a lot. But we're going to start to see what this looks like in 2 variables. And, of course, there'll be calculus in 2 variables. Now, like I said here, this is kind of a summary. It's not doing a deep dive at this point. So you might say, here are some interesting parametric curves. And you may say, what are you talking about? This curve, the points in your xy plane for this curve, is given that the x coordinate is represented by cosine of t, the y is sine of 2t, but then you say, Mr. Judge, where's your orientation? I'm sorry, where's your t interval? Well, this example, if it's not listed, that means t is any real number. And so you might start to wonder and say, well, how is that t value oriented? Remember, t is any real number means negative infinity is less than, it can't be equal, is less than t, which is less than positive infinity. So I can kind of sketch an orientation if I wanted. I can say, okay, what happens? Well, we don't have to go that far, but I just want to mention this. You're looking at a curve that you may not recognize. It looks like a bow tie to me. Do you guys understand what I'm saying? If I look at it, you say, what's the name of that curve? I don't know. It doesn't have a name. But it looks like a bow tie. But notice the curve is a lot more complicated than anything you've ever seen. You haven't seen this in the XY plane before in your life, this curve. Can we represent it? Maybe, but if we did, the algebra is sophisticated. And in fact, if we did calculus with that, it would be a lot more difficult to do. So what happens is, for some of these curves, believe it or not, the calculus is somewhat easier. Like if I said, could you guys find the area? Here, one day we will. Can you find the area here, the total area? One day we will. Can you find the equation of the line tangent to the curve at a particular point here? Yes, one day we will. In other words, one day we'll do the calculus for these curves too. But we first have to learn about what these curves are before we could do the calculus of this, because we're adding a new variable. So that's why I ask, have you guys ever seen parametric equations before? You know, so I'm kind of introducing some of this stuff to you guys here, right? Here's another curve where x is 2 cosine of t, y is t minus cosine t, and then t goes from 0 to 2 pi. Now, here they gave us an interval of t now, okay? So if they give us an interval of t, can I ask you guys, what's the initial point? You let t be 0 here, so plug in 0 for t. What do you get for your x value, right? You got to know what 2 cosine of 0 is. What's 2 cosine 0? Isn't that 2? Okay. So it's kind of simple in a way. Well, what's the y value then? That'll be, well, maybe, I don't know. Let's see, 0, right? We get what? 0 minus cosine of 0, and you're right. Looks like y is negative 1. So the x coordinate is 2. The y coordinate, this is the coordinate, 2, 1. It's negative 1. I apologize. No wonder I couldn't find it. It's like, what's going on? Is there another typo? No. And that happens when t is 0. So there's your initial point of the curve. Now, how do you guys think you get the terminal point? What would you do? For t, what do you plug in? 2 pi. What do you get for x? What's cosine 2 pi? Isn't that 1? What's 2 times 1? Is that 2? So x is 2. So y will be 2 pi minus cosine of what? 2 pi. So this will be 2 pi minus 1. Now, what is pi approximately? About 3. So 3 times 2 is 6 minus 1. Isn't that 5? But it's a little bit more. Here's my point. Terminal point happens when t is what? 2 pi. So as you go from 0 to 2 pi, all these points are plotted this direction because you start at that initial point and then you end the other point. So you're really looking at what's called the orientation of the curve. You can find the orientation, and that's how we notate it. We just put those arrows. So all the points are thought of as being plotted in this way. You go, okay, start here. Let me get the highlighter. Start here, here, here. This is what happens as t goes from 0 to 2 pi. And then you end there. And the point being, you really end up with this nice smooth curve. Well, not smooth, but somewhat. I got to be careful with my language because smooth means something in math. But I just want to go through some of the details here with you guys, how to start to sketch these things. Okay? And then you look at this curve, and this is a little bit more sophisticated. Okay? But notice what's going to happen even one day here. What's going to happen one day here, just to go back to this curve, to talk about a little bit of the calculus of this curve. What's going to happen one day in our future is that they're going to even ask you what's the arc length of this curve. In other words, if we can open the door, we got somebody coming in. So in our future, we're going to be able to do some calculus with this. You say, what do you mean? Yeah, they're going to ask you, hey, what's the arc length of that curve? What's the length of the curve? We can find the length even of a parametric curve. We can do calculus with parametric equations. So that's where we're headed. And this will be in 2 dimensions, and then calculus 3 kicks it up to 3 dimensions. And so you can find a length of a curve in what's called 3 space, 3 dimensions. Anyway, I think it's kind of nice. We can even find the length of this curve with calculus. That's where we're headed. How do we get the initial point? Right? You plug in the value for -2 and find where it starts. So it looks like it's going to be, if I plug in -2, negative minus, it's e squared is about 9. That's like 7. So it looks like to me, just so you guys know, my initial point might be over here. And that happens when t is -2. And t is +2. Get your x and y coordinates, plug it in. Looks like e to the -2 plus 2. Well, e to the -2 is like 1 over e squared, like 1/9 plus 2, 2 on the 9th. So I can already see over here, this is my terminal point. Okay? Happens when t is +2. And I bet you this is when t is 0. Yeah. That'll be 1, 1. Yeah, so this happens when t is 0 here. So you say, what's my orientation? Well, we go this way, this way, this way, and this way. And, you know, one day we'll be able to take that curve and do a lot of things with this too. Find the equation of the line tangent to the curve at a point on that curve. But we can generate the x and y values by looking at different t values. So you just do a little bit of the arithmetic, plugging it in. And then, you know, believe it or not, like I said, a lot of these curves are a lot more sophisticated than you think. Like this curve, this is a lot of complexity to this curve. It's defined as x being t plus sine 2t. For the x coordinate, the y coordinate is defined to be t plus sine 3t, where t goes from -10 to +10. And you can probably find, again, orientation of that curve. -10. So it looks like to me, if I plug in -10 here, -10 here, you know, sine of 20, well, sine is between -1 and +1. So it's not going to change that much. Here's my point. It looks like this will be my initial point. And then this will be the terminal point. And again, it happens when t would be -10. And that happens when t is +10. And I bet you that happens when t is 0. If I plug in t being 0, yeah, sure enough, we get the origin. The x coordinate is 0. The y coordinate is 0 if we plug that in for t. And so we can kind of see an orientation going this way. See what I mean? So, you know, that's kind of a very fascinating curve. I wonder what the arc length of this would be. You know, might have some interesting ideas, but anyway. And then this is a more sophisticated curve. So there's a lot of curves we can create using parametric equations that are, you know, a lot different than what you've ever seen before in your life. So parametric equations really kicks our life up into a lot of ways. Okay, you guys know what I'm saying? Look at this curve. This is a very famous curve in a calculus course. People care about this curve with some applications. You might say, what's my t value again? Well, if they don't have t listed, t is any what? Real number. Meaning it's that interval here. From -infinity to +infinity. And you say, what does that mean? Well, my t value is between these two numbers, but it's never equal to those because it's infinite. It's not finite. There's no initial point. There's no terminal point because t is, you know, it's over the whole real number line. So there's no initial point, no terminal point here. Okay, you guys okay with that? So this is another important kind of curve that you'll see as examples in your book. And then you kind of see this too, to say this to you guys, this example. We can find, what is this called? If you say to you, we're really getting back to a world we know about. These curves, you've never seen them before. They have some of these curves have names. This has a name. And this, I don't remember what this name is. Some of these curves have formal names. Mathematicians that actually, you know, I don't want to say discovered them, but maybe yes. But some of them have names. They're famous. You say, well, how do I ever learn some of these names? Well, you might learn it. For example, you will go to graduate school and it's graduate level mathematics to some degree. You start taking a lot of these other courses and you will definitely dive into some of these things. But we're just going to actually do some calculus with these curves. That's what we're going to do. So we got to keep it simple, but there's a lot more details that you can see. Like here is just a simple line segment. So you say, what's a line segment? Do you guys remember what a line segment is? It's just a line segment is just when you go from point A to point B. That's a line segment. Well, we see this in Calculus 3 as well. Line segments. You study this in Calculus 3. Line segments in 3 dimensions. This is in 2 dimensions. Remember, geometry is in 2 dimensions. Your XY plane. Length and width only. Your paper, that's 2 dimensions. So if you said, okay, this is a line segment, it is, and I'll even label that. Where's your initial point? Well, where does this start? If t is -2, the starting point, x is -1. So I already know where x is -1. It's over here. Is that right? We can plug in the y value, and we get 5, really plus 4, which is 9, and that makes sense. In other words, I start my line segment here when t is -2, and then where's the terminal point? Well, plug in 3. 1 plus 3 is 4. And then 5 minus 6 is -1. So I already know over here, the address here, this happens when t is what number? 3. So the orientation is this way. Because initial is where you start, terminal is where you end. So we have a lot of interesting information here. So you'll see this kind of stuff again in 3 dimensions in Calculus 3. But notice the following too. I'm going to say to you, what is L? You say, what do you mean, what's L? Well, L is a line. It's the line that this really represents. I thought I was going to be able to do a 2 arrow, double arrow. This is actually, technically, what I'm drawing here, the highlighter is a line segment. It's not even a line. But I'm trying to draw a double arrow. So that's the best I can do. There's now a line. So like from beginning algebra, how do we find that equation of the line? Do you guys know? That's kind of something that is studied in this section too. How do we find that line that we labeled L? Right? We start with a parametric equation that y, or x is 1 plus t, y is 5 minus 2t. Okay, so if I want to find what that line is, what do you think I can do? Do you guys know? Yeah. So you've seen this before, these things? You guys know what I'm saying? Because usually when you talk, how many people in the room have seen these parametric equations in your life? Nobody? Some? I know people get afraid to answer that question. But like I said, it's like if you've seen it, it'd be interesting to know where you've seen it. Trig may have it. It's optional in a trig course. It's optional in a pre-calculus course. But it's not optional in a calculus 2 course. So I got to talk about these. And in the past, I used to assume people studied it in trig. So I can solve that for t, is that right? And then I can substitute. So what was suggested is solve that for t, plug in the t here, the x minus 1, and so you get now y is 5 minus 2, not times t, but x minus 1. So you're going to use substitution. Yes. Solve this for t. There you go. And plug that in. And then do a little algebra, right? You go y will be 5 minus 2x plus 2. Or y will be, what's 5? This will be 7 minus 2x. So this is the beginning algebra equation in blue. Even though that's not what you really have, you sort of have it. You don't have a line, you have a line what? Segment. What's the difference? A line segment are points on a line that have an initial point and a terminal point. From geometry, this is how they draw the picture of a line segment, right? Line segment in geometry. AB. That's a geometry version of a line segment. Then if I said to you guys, what are you guys looking at here? What do you guys think you're looking at? What do you guys think? What is this? What if I square x? I get x squared is going to be t. Is that true if I square both sides? Right? So what does that mean about y? Y will be 1 minus, this is my point to you. There's t. There's t. So let's substitute. Y is 1 minus x squared. So that's a parabola that looks like this. Is that true? But you might say, but Mr. Judge, you only have half the parabola. Why? Why, parametrically, is this only half of the parabola? Because they didn't tell you what t is, did they? But what does t need to be? T has to be greater than or equal to 0. Why? Because of the domain of what x should be. The domain of x, t has to be greater than or equal to 0. We don't have imaginary values here. So if t is greater than or equal to 0, that means x is greater than or equal to 0. So the domain of t gives you the range of x. So where are positive values of x? Positive values of x are all in this plane here. You guys see my point? Those are all the x coordinates that are positive, everything to the right. To the right of the y-axis, x values are negative. Yes? Would that mean that the domain would be 0 to infinity? Yeah, actually, it's 0 to infinity. So, yeah, what that means about t is 0 to infinity. It only has an initial point. It doesn't have a terminal point. And the orientation looks like this, by the way. So, there's some detail about that parametric curve. So, and we also know the equation. So, sometimes that's fun to do. It's fun to know that equation. So, I have to introduce to you guys this idea here of what parametric equations are. X is a function of t, y is a function of t. And a lot of times, it depends on the question. If it's especially chosen, you'll be able to understand what that curve, where that curve came from. But you might say, well, what do you normally do with this? Well, normally you plot points. Like in, if you remember like high school or middle school or elementary school, I don't know. They taught you Cartesian coordinates by plotting a whole bunch of points. And you did that like all period long, plot points. You got sick and bored. That's what I did. Well, you still plotted a lot of points. But what I'm saying is how you really introduce this from first principles is you tell people, let t be this, these values, give me the x coordinate, give me the y coordinate, plot the points. And then after a while, you see the points form a shape, and then you go, oh, it looks like it's doing this. That's the same kind of idea in theory for parametric equations. But everything that I did here was computer generated, to draw you a nice picture. So, there's kind of different I don't know how to say this, but back in the day, they used to give you these equations, and then they would say sketch the curve. And you would go, oh my God, I don't know what that looks like. How do you sketch this curve? Right? They wouldn't do that for the earlier examples I showed you because there's no way you can do that really without a computer or without technology. But when you first start with some of these curves, this is how they have you guys start. They go, here you go, x is sine t, y is cosine t, t goes from 0 to infinity. I'm sorry, 0 to pi. So there's an initial point and a terminal point. So how would you do that without using technology? Right? I'm even trying to remember. What technology did I use? I might have used Desmos. God, I love that Desmos. I love Desmos. Huh? Jesus. You guys know how to sketch that curve? If you didn't have Desmos, what would you do? You square both sides. Would you get x squared is what? Sine squared t. You square both sides for y. Y squared is cosine squared t. Square both sides for the x and y equations. And then what do you think you do? X squared plus y squared equals, what do you get? Sine squared t plus what? Plus cosine squared t? Let me do that. Do you guys know what the right-hand side equals? What does that right-hand side equal? 1. How do you guys know sine squared t plus cosine squared t is 1? Pythagorean identity? It's a Pythagorean identity. Let me share with you guys an interesting thing that's going on here, right? See what you guys think. You guys took Calculus 1. Is that true? Okay. And you guys passed Calculus 1. Is that right? Okay. Let me ask you guys this question here because it reminds me of this Pythagorean identity. X squared plus y squared is 1. What does that represent? Isn't that a circle centered at the origin, radius 1? You go, okay, Mr. Judge, why don't I have a full circle? You guys know why you don't have a full circle? Well, the parameter they gave you, 0 to 0, t goes from 0 to what? Pi. So here's the full circle. So you go, okay, what does the rest of this look like? What happens when t is 0? What is sine of 0 and cosine 0? Sine of 0 is 0. What's cosine 0? 1. So the x-coordinate is 0, and I think I didn't draw it correctly. Yeah, there's a typo. I got to fix this one. Where is that initial point? It's right here. I really know the real typo I did. You want to know what the real typo is? Here's what the real typo is. That was really cosine of t, and this is really sine t. It doesn't matter, but it kind of matters. So if I change that typo, there's my initial point. Now the curve makes sense, but the algebra is still the same. So I think I'll just do that there, right? T is 0, 1, 0, and then what do you think this will be? This is t is pi. So I'm thinking when I get home, I got to remind myself, fix this stuff because that's really bad. 3 typos already. But it was during the pandemic, and I was doing notes for every class. Your orientation looks like this. So I'll fix those 2 typos. But that's what happened with this curve. So this one's cosine t. This is sine t. The algebra is still the same. It's still a circle centered at the origin, radius 1. But back to this point I want to make to you guys. What are the chances do you think you would have To pass Calculus 1, if the highest math course you took was geometry. High school geometry. What do you guys think? Anybody here try taking Calculus 1 and you only took high school geometry? Pass with a C minus. What are the chances of passing a Calculus 1 course would be? What do you guys think about that? Low? How low? How low do you think it would be? Well, there's a report I got. The state gathered data, and they said, "Oh, students that from the small study they did, who only completed Geometry 1 in high school, had a 33% chance of passing Calculus 1. 1 in 3. Does that make sense? It doesn't make sense to me. I'd say your data's bad. The chance of passing Calculus 1 with only high school geometry is 0. But the state's pushing this idea. No, there's a chance they can do that. So you might see geometry students in Calculus 1 only. So in other words, they skipped intermediate algebra. Did you use any algebra in Calculus 1? They skipped intermediate algebra. They skipped trig. They skipped pre-calculus. And somehow they had a 1 in 3 chance of passing Calculus 1. I have no idea. Well, there's a lot of lurking variables. That's called a lurking variable, meaning, hold on, give us more information about what was going on with that picture and that data. Because scientifically speaking, if you have an experiment, that's called an experiment. If you have an experiment where you let students who only completed Geometry 1 into a calculus course, and you say 1 in 3 will pass, then you have to repeat that experiment elsewhere and see the same results. You guys know what I'm saying? This is scientifically speaking. You don't draw conclusions unless you can peer review an experiment and reproduce the results. That's just how it works. You got to reproduce those results. I doubt you can reproduce those results. And those results have to be reproduced everywhere you go. Can't be, so in other words, there's more to the story, and we don't know the more to the story. It probably isn't repeatable if it even happened in the first place. Yeah, it might have been 3%. Or the typo should have been a 0%. Because I got news for you. There's no way anybody can pass a calculus course without algebra. Calculus 1. Stop and think. Did you do Calculus 1? Could you have passed it without algebra, trig, and pre-calculus? Now, you know what the rate was for pre-calculus students? Meaning, students that took pre-calculus and passed it in high school, you know what their chance of passing Calculus 1 in college was? 44%. So it's only about 11% more? Something's wrong with that study. Remember, you got to reproduce this results everywhere you go. Interesting thing. What do you guys think? Does that kind of make any sense to you guys? See, you should understand this because you completed Calculus 1. You should understand what I'm saying to you. Could you have completed Calculus 1 without pre-calc, without trig, without algebra, intermediate algebra? I'd say the chances are pretty nil. I want to see the test. What test did they give them? Did they just give them the power rule for x squared and a derivative? and said 1 and 3 answered the question because it's arithmetic? You guys see what I'm saying? We got to see that test. Would that be a test that Calculus 1 test that you would see in maybe UCLA? Do you guys know what I'm saying? Because all those 3 systems have the same courses that articulate. So it's an interesting report. Maybe I'll share it with you guys. You guys can read it. Anyway, reminds me of this. There is some trig you need to know to answer some questions. You guys see what I'm saying? Here's a nice circle. How do we know this is the equation of the circle? What happened with the parameter t? And in all honesty, I know what I did. Even though that's sine t, cosine t, and it doesn't matter, it matters only for some intervals of t. If it's 0 to 2 pi, it ain't going to matter. It's not going to matter, 0 to 2 pi. You can have sine, you can have cosine. You want to draw the right picture is what I'm saying. You want the picture to be correct. And so I can change this, I cannot change this. It won't matter because now squaring both sides and adding them is going to give you the same thing as you did before. It's just your initial point is going to be the same as the terminal point, wherever that is. So if I just keep this picture, I will. Sine is 0, cosine 0. That is 0, 1. T is 0. And if I replace t with 2 pi for both, that's the same location. So in other words, your initial point is going to be the same as the terminal point in this picture. But what about the orientation? Up here, it's simple to do. Down here, we still got to do something more. How do I find the orientation for this picture? Because like I said, orientation is important. It's going to be probably more important in Calculus 3 than it is in Calculus 2. But in Calculus 2, we introduce it. But I want to let you, I want you guys to see that, you know, so when you go to Calculus 3, you know what you're doing. Okay. How do I get my orientation then? You need to use a t value that's what? Between 0 and 2 pi. Find where the point is. And maybe it's an easy situation. Use t as pi. We know, what is sine pi, by the way? Don't you got to know a little bit of trig? Okay. Sine pi, what's that going to be? Is that 1? Negative 1? 0? Sine pi is 0. Okay, what's cosine pi? So where is 0, negative 1? X is 0. Y is negative 1. Is that true? That's down there. That happens when t is pi. So how's my orientation? It's probably not a good value of t. Because what's the deal? If I started here, I could have got over here with pi, right? Or if I started here, the other way. See what I mean? So I'm going to have to use another value of pi. What should I use? I'm going to probably try, should I use pi over 2? So what is sine of pi over 2? Sine of 90 degrees. Isn't that 1? So that means x is 1. And then cosine 90 degrees is 0. So this point is 1, 0, right? And that happens when t is now pi over 2. So my orientation is going this way. What kind of orientation is that? Is that clockwise or counterclockwise? I think that's a clockwise orientation. Is that right? So t is pi, t is 0. We're here, 2 pi. Oh, we're back. Excuse me. Pi over 2. We're over here. For that value of t. So t is pi didn't really help us. T is pi over 2 helped us a lot. We can figure out the orientation. The orientation is going to be here clockwise orientation. So it's sketching the curve clockwise. So that's that's always a fundamental shape that's fun to work with and learn about when you're working with parametric equations. They start with this. They always start with those. And then this is another line segment, and I'm going to say to you guys, this is another interesting situation. You say, why is that so interesting? Right? Why is that an interesting situation? Do you guys know? It's a line segment. It's not a solid line, is it? It's a line segment. You know, you're between these 2 points. And then t is any real number. So t lives between negative infinity and positive infinity. Okay? But what is happening with this curve? You guys know what this... The line of this curve is very simple. You just add x and y. It's going to be sine squared plus cosine squared. But what does that equal? That equals 1 by the Pythagorean identity. So x plus y is 1. And what you guys know is that's an equation of a line. Graphing form is y is 1 minus x. So it has a y-intercept at 1. Here's where 1 is, the y-intercept. It has a slope of negative 1. So this is also 1, by the way. It's downhill. But that's the line they're talking about, okay? But this is a line segment. It's not a line. So if I said to you, that's where it came from, but it's a line segment, you know, x is sine squared. Y is cosine squared. T is any real number. How do I talk about the orientation? T is any real number. T could be 0. When t is 0, what's x? Isn't that 0? This happens when t is 0. Sine squared of 0, that's sine of 0, which is 0, 0 squared. So my x value is 0. And then cosine squared of 0 is 1. So this happens when t is 0. I'm right here. But I don't have an initial point. I don't have a terminal point. So my point about this is this. Your orientation goes back and forth forever. So when they sketch this curve, what happens is for the various t values, and you would say, well, what about the orientation? Well, it might be you're sketching that and then you keep coming back. It just repeats forever. For every t value. This goes on and on forever. And that's what you're sketching. So the orientation, because t is any real number, you can't give an orientation. It's an important small detail. So that is oscillating, you know, for all t values, you're oscillating along that line segment. That's why it only sketches a line segment. So if you put this in a computer that graphs and say, I want x to be sine squared, y to be cosine squared, this is what the computer does when it sketches it. It uses various t values and plots it. It's a computer. It does simple things very fast. So I can do it slow, but my point is it starts at some t value, whatever that program does, and it just starts plotting all these points until it ends at some t value, really. But you know, t goes from that's why it's a line segment. You know, it's a small detail. It's an important detail. This This starts at 0, ends at 2 pi, and that's it. But it's still, t is over an interval. And anyway. And then what is this? You go, oh my God, Mr. Judge, what is that curve? X is secant, y is tangent. What does that look like to you guys? T is any real number, by the way. But what does that look like to you? Why is that a hyperbola? Anybody know? How do you show? Because back in the day, you know what they would do? They would do something mean and say to you, hey, x is secant of t, y is tangent of t. Can you sketch this curve? And you go, what? And you didn't have a calculator. Is this cosine? Is that right? What is tangent? Sine over cosine? Maybe that's not it. I know what I'm going to do. You know what I'm going to do? I'm going to do what I did before. What's x squared? Okay. What's y squared? Is that right? Is there any Pythagorean identity, ladies and gentlemen, that relates secant squared and tangent squared? I might have to go back to my trig class. How did those students pass Calculus 1 without trig? You guys see what I mean? It's not something you just say to people who, guess what, use this, and they know when they'll use it forever. They got to study these facts. Right? Where's our secant tangent? Do you guys remember? What do we know? Tangent squared t plus 1 equals secant squared t. Is that right? So what does this mean? You guys should be happy with this. You know what this means? Let me get some colors. Secant goes here. What is that really? X squared. Tangent squared goes where? Right here. What is that? Y squared. So this means y squared plus 1 equals x squared. What that means is x squared minus y squared is what? 1. So back in the day, they would say, hey, graph this. And you know what you had to do? You had to do a little bit of algebra and trig. Use a trig identity. And then you got to remember, hey, what's x squared minus y squared equals 1? Well, that's an equation of a what? Hyperbola. Okay? You may not agree, but I've said, take a look. Do you agree now? Do you guys remember the general equation of a hyperbola? You learned that in intermediate algebra and in pre-calculus, because it was x squared over a squared minus y squared over b squared. In fact, that's a horizontal hyperbola where a is 1, b is 1. There's a graphing technique that you use in those courses to graph conics. That comes back in calculus, 3, by the way, So that's how you had to sketch this, because you sketched a hyperbola in your life. So you go, oh, that's really a hyperbola. There you go. Isn't that the same one? Why do I have that? That's a little goofy. Is that sine squared cosine squared? Huh. Same curve. I must have been very. Oh, this is another favorite of mine. How do I know that's an ellipse? It's another favorite of mine. How do we know? If I square both sides, don't I get this? And if I divide the first one by 16, both sides, don't I get this relation? Do the same thing for the y squared. The y squared divided by 9, right? And that's going to be what? Sine squared t. So, back in the day, they would do the same thing. They'd say, hey, here you go, and do what? Sketch this curve. T is any real number. There's no interval. What do you guys do next with this now that you've seen the circle? What does that mean for you? Take x squared plus 16 plus y squared over 9, and what is that going to equal? You can say, is that cosine squared t plus sine squared t? Yes. What does that equal? Isn't that 1? So the very reason why you might say, hey, that looks a lot like what? Well, not just looks a lot like. This is the equation of an ellipse, isn't it? What's the general equation of an ellipse? X squared over a squared plus y squared over b squared equals 1. And so there's your ellipse, ladies and gentlemen. Anyway. And then what I did is you drew a portion of an ellipse because now you have a initial point, right, and a terminal point. You guys can figure what that out is. So what I did is I said, okay, here's your ellipse. What happens now when they give you an interval and you can find the initial point? Cosine of minus 90, right? What's 4 cosine minus 90? I think that's the same as cosine of 90. What's cosine 91? So what is x equal? You guys could double check this. And then this is an interesting question too. You guys can find your initial point and your terminal point. Cosine of pi. What's cosine of pi? Negative 4? I'm going to do this. Terminal point. And is this the initial point? Cosine of minus 90 degrees. Oh, that's 0. Is that 0? What's sine of 90? Or negative 90? Yeah, so this is, so in other words, here you go. Here's my orientation. T is pi. Yeah.
If we see that, would we be wrong to just look at it and assume that because that's a negative pi half, it would start at the bottom?
No, be careful. Because it doesn't start at the bottom because t is negative. You got to plug in the numbers here for t. And then this, in case you guys didn't know what this is, what is this? You guys know what equate? You might have seen this in calculus 1. Isn't x to the 1/3 t, y to the 1/2 t? X to the 1/3 is y to the 1/2 because these are both equal to t. And so you say, how do I get y? Well, square both sides. This is x to the what? Y is x to the 2/3. So when I see this question, I remember that question in calculus because of this very special, this is a calculus 1 kind of thing. If t is negative 2, x is negative 8. Initial point. T is negative 2. Terminal point. T is positive 2. What's going to happen is this is where t is 0. Now, why am I thinking of calculus 1 with this? Does anybody remember? Why is this a big memory of calculus 1? When did you study this curve? Y equals x to the 2/3 power in calculus 1. This is a very special curve that came up in calculus 1 with the topic. Anybody know? What's special? What's so special about that point? Anybody know about that? That's where your function is what? It's not differentiable. How do you know the function's not differentiable? So looking for your test. You guys remember? Whenever you have a corner, it's not differentiable. That's where the derivative around 0 did not exist. So in calculus 1, I know when I went through that stuff, we looked at the derivative for that function around 0 by using the definition, and we showed that we got it does not exist at this location for x. So you might say, why are you bringing up all of that stuff? Well, because it's, again, you can do the same things with these curves in parametric form. But we don't know the calculus of it. So all I did today, ladies and gentlemen, and you can look at this one. This is a nice equation of the circle. Centered at 2, 3. Looks like radius is 1. And you could derive that as well, So I went crazy here and I did a whole bunch of parametric curves for people to show them where they came from. And you could get all of these equations here for these. A couple more of these equations. This is a parabola, by the way. You can show this is a parabola. It does have an initial point, terminal point. This is a sideways parabola as well. That one's very easy to do as well. Right? That's x is y squared. It has initial point, terminal point as well. And has orientation. But what you'll do in your future, we're going to do with starting tomorrow, calculus of parametric curves. So I just wanted to introduce these parametric curves to you guys. Anyway, I'm going to pass back your test and your in class portion, and it's out of 125. I'll pass that back out to you guys, and you guys can get started on at least reading. If you go back to the browser, you might want to get started on reading what? Where are you, browser? Oh, this is something I did for the trig students. To introduce parametric curves for the trig students. How to plot points. You're plotting points there, and they go, oh, okay, this is where these things come from. And then somewhere down the line, I think I started to do something more like what I was showing you guys today. So these trig students get to use algebra to find the curves. That's for the trig students. Anyway, you guys can kind of read some of that, and then we'll do the calculus of parametric starting tomorrow. So, okay, we'll pass this out to you guys, and I'll see you guys tomorrow.